What do you? Every live, yeah, trying to think like because you have that. Then like every
Where does that say?
All
right, guys, page 45. Okay, so we briefly talked about how we can build the area of a region by polar curve by involving basically taking that sector area formula and kind of splitting it into the sum of infinitely thin sectors, and then creating an integral definition out of that. Okay, we did number 1 and 2, right? On this page. Okay, so let's go to, yeah, so we'll spend most of our time just going over this. Yeah, I think yeah, I don't think we need to jump into the area bounded by 2 polar curves till tomorrow. So we'll spend most of our time today. If we have time, we can always go to the next topic, but we definitely want to get more comfortable with this before we move on. So page 46. All right, number 3, it says find the area of the inner loop of Lima sine of 2 cosine theta plus 1. Really, the area formula is not too bad to create. It's just having to figure out what the bounds are. And basically, the area of the inner loop, it's going to be between your polar zeros, right? That's where, once that polar zero hits and the polar zero hits again, that's when it's going to end up closing off that loop for us. So to find the bounds, we're going to figure out where find the 2 polar zeros. That's really the only challenge here. If we can find that 2 polar zeros, then setting up is going to be pretty easy to find the area. So my R is 2 cosine theta plus 1. I'm going to set R equal to 0, figure out when is radius 0. Okay, so where's cosine equal to negative 1/2? And yeah, second and third quadrant, right? So here's our area formula. Set that up and then just plug in the calculator. Any questions? Number 4, same idea, find the area of one petal. So we just have to figure out where the two polar zeros are and make sure we're going from polar 0 to polar 0. Okay, so gotta be careful here. We don't want to assume that theta equals 0 is a polar 0. Sometimes it is, but if it's not, then we want to start in a place where we go from polar 0 to polar 0. In this case, if I plug 0 in, 3 cosine of 0 is going to be 3. So the graph actually starts here. So, and it goes from here and it builds. So say for if we just go from polar 0 to polar 0. We can set this up by hand. Right, because sometimes the graph starts at 0, sometimes it starts away from 0. So we want to make sure that we're grabbing the correct data, right? So if we're now we can still find the area if it starts here. I'll show you where we use symmetry to get there, but I want to do it first where we just find the polar zeros and just look at what's between the polar zeros. So if we do this by hand here, cosine 3 theta is equal to 0. In other words, if I solve for 3 theta, we can figure out first, where's cosine equal to 0, and then we can divide by 3 to get to theta. So let's list out a couple of places. Where's cosine equal to 0?
Pi over 2.
Mm-hmm.
Pi over 2.
Yeah. Keep adding 2 pi to get to the next value, but this should be enough, right? Divide by 3 is same thing as multiplying by 1/3. So we know that pi over 6 is a polar 0, 3 pi over 6 is a polar 0. And then if we know that we have consecutive polar zeros, we know that action will cut off and create one full petal. So once we have 2 polar zeros, that's enough for us to create our area. Oh, and then just to let you know, you don't have to be in polar form to create this formula. You can be a rectangular form and just do 3 cosine 3x dx from pi over 6 to pi over 2, and it'll still get you the same answer, right? It's just if you want to see the graph, you want to be in polar form, but if you're just entering into the calculator integral notation, doesn't matter if it's x or theta, you're going to get the same answer. Any questions here? So I want to show you a different way. It's not necessarily a better way, but I do want to help us see things from a different perspective in terms of, oh, there's all these symmetry involved. A lot of times we can just find out half of something and then double it, and that will get us the same answer. Just want to give you some, different perspectives to, in case, let's say you did a problem one way and you're just not sure if that's correct. You want to do it a different way to kind of check your answer. I just want to give you another way of doing things here. What if we wanted to find the area starting at 0? Okay. So 0 is going to start here. Okay. And then from 0, where's that polar 0 going to appear if I start at 0? It's going to first appear where at pi over 6, right? It's gonna come in this way. Can we find the area of the pedal if we just have 0 and pi over 6 to work with? We can find the area of this region and then do what? Just multiply by 2. Okay, so I just want to just, show that we could do this from 0's perspective. Integral from 0 to pi over 6. That will fan out half of the pedal. So we get this, that ends up giving us 1.178 multiplied by 2, or we can get the 2's and 1/2 to cancel out and just do the depth integral. That'll get you the same thing. Okay, so I think for the rest of the period, I just want us to get as much practice from problem to problem. So good to have you guys start, and then I'll show the answer and I'll go through it, and we'll just do that for the rest of the period. Okay. And then you can also use the period to basically get your homework done for as well. All right, so let's move on to number 1.
Set it equal to 4 when all the others we say equal to 0.
Um, well, I think I messed up. I think that should be 0. Sorry, let's see.
It's -1 and there's only 1.
Yeah, hold on a second. Why did I do that? Where's my cardio?
You go 4 to 4, Mr. Grant.
I'm sorry.
Yeah, you go 4 to 4 for the one rotation.
4 to 4. What do you mean?
Again, like you said, the radius equal to 4 twice, then that'll tell you at what point it makes one.
Right, one full cycle. Yeah, so I think this is also just, if we just use previous knowledge of what we know about cardioids, that cardioids is going to complete this full cycle between 0 and 2 pi. We can jump directly to this, not having to set that. But basically, we know that using using a table of values, yeah. Right, but right, if we, yeah, it keeps going. So from pi to 3 pi, it'll do half the cardioid and then do the other half the cardioid. So as long as you go from 0 to 2 pi or pi to 3 pi, or as long as it has a 2 pi interval, it'll get that area eventually. Yeah. Yeah. So yeah, because we know the graph is going to start here, we're just asking where else is it going to start? It's going to hit that point again. That's why. I think because we know that 2 plus cosine theta starts at 4. Where else is it going to start? Where else is it going to hit 4 again? It's going to hit 4 again at 2 pi. So that's a way for us to know that, okay, that full interval is from 0 to 2 pi. But at the same time, if we just remember that cardioid does have 0 to 2 pi, we don't have to do that check. Yeah, so basically anything that's limmason or cardioid or cardioid with inner loop, they're all going to have full cycles from 0 to 2 pi. Circle is from 0 to pi. Odd numbered petals is 0 to pi. Even numbered petals is 0 to 2 pi. Yeah, so I think for petals, I always like to set equal to 0 because I'm just looking to see, okay, where do I see 2 polar zeros occur back to back? Then I know that a full petal is going to be enclosed, and then that's how, yeah. So I think for petals, I set equal to 0, but for limmasons and for circles, I just remember that my cycle is either pi or 2 pi. The reason why I set it to the radius is because I just want to know where I start.
Yeah.
If I start at 6, 0, 6, then I want to know where else am I going to hit 6 again. So that's why I set the radius equal to 6 for number 3. Right. I plug 0 to see, okay, where am I starting? I'm starting at 6, so I want to figure out where is the graph going to hit 6 again. Yeah, anytime I'm looking for inner loop, anytime I'm looking for a pedal, I'm always setting go to 0 because I want to know where is that region going to close itself off again.
For help, it's like. For help. You like. Like shorts and and then I did like. It's not gonna be so complicated. I look at you do this.
Yeah. Everybody okay with 3 and 4?
On a test, would it tell us, what shape it is along with the equation, or would it just tell us to find like the area of the equation?
No, it's actually to find the area of the equation.
Okay.
Yeah, yeah. Yeah, definitely want to use your calculator, practice, with the notes that we have, that we've gathered, and then also use the calculator to help you figure out what that shape is, what the properties of those shapes. Yeah.
Can you graph the limit state on your calculator or no?
Oh, this one, I think you may have to break it up into R equals +4 cosine 2 theta and R equals -4 cosine 2 theta.
Or like the square root of that or?
If we do this square, well, I think it needs to show up. I think you need to create 2 different R equations. I don't know if it'll do it all in one go.
Is that what the R equals, or does R equal the square root?
Well, we're talking about an equation here, so R will be equal to plus or minus. You're right, sorry. You're right, square root. Yeah, plus or minus square root.
I'm trying to keep up my calculator and
It didn't show.
it didn't show.
Okay, let me see.
Quick for number 3, why'd you set it equal to 6?
Because we're starting at 6. And we just want to know how long does it take before it hits 6 again so that we know that a full cycle has been reached. But if we know that a limacon is going to have a full cycle from 0 to pi, we don't have to go through this step. We can jump directly to this. Yeah, it doesn't quite get it perfect. Yeah, no.
But I don't think you need the second one. 'Cause it just-
Right. It's just asking for the first one, right? So we just know that polar zeros is at pi over 4, 3 pi over 4. That's enough for it to close off one region, and that's enough for us to get our bounds for our problem.
It looks like those two graph the same line. The one you wrote over there.
Let's see.
Oh, actually, that makes it this next flip, so it goes around and overlaps with all the equation.
Let's see.
Just my text and origin. Negative on, then you're just like Fluffy butterfly. So it would like, just allow it to data.
And then here, because back over like this R squared d theta, you could replace that whole thing with one.
They're supposed to be data coverage. Zero, which goes straight. Yeah. Maybe that's smaller, so there's this probably.
Do I have to figure out?
But like,
X?
so if it's smaller.
Can I look at it? Say you make sense for that.
Well, right, just have. Graphic.
I can do this, but am I supposed to do it or it's just looking at the calculator?
Secret. Because
Because that means that the derivative is like independent of itself.
Right.
So am I,
and since it's minor zero, then it's just like. But on the greatest.
because I guess it's
R,
so
so it's that's just the minus R.
like it's like one of these. Right? So
Well, normally I would say we eliminate it because it shows up under two, under both X prime and Y prime, but.
It could be the derivative. It's got that in calculator.
Shouldn't zero also be like that? I don't know why I guess without zero.
Yeah, how much of it? You know what I'm saying, you know, we can honestly. This is the still.
For something.
Like right, raising that. Is sliding, so like, yeah.
Yeah, we should look at the graph as well. I think technically I removed them because it also showed up in the horizontal tangent, so it needs to be removed. Also, yeah, you're right. You can look at the graph and tell that this is not.
so we get the, we get the.
Yes, you can calculate for the whole
No,
thing.
for the part of the AP.
It may not, but I feel like if it's asking for horizontal tangent, technically we should be looking for X prime as well. Make sure that X prime doesn't conflict with this and then use that. So I didn't show that step.
Okay.
Yeah.
I think the graph. Okay. So, you go, these are the, by default, your data bank. Just by putting.
So it's just, okay. Also or if it is interval too wide where it's not getting to those smaller controllable points. Let's see, where,
Before was that like six, like too high, actually, yeah, that's too high.
uh,
And so, since too high to cover it all, I just increased it to above too high.
so it had to go all the way to 99 to get that.
You can pick the lower number, that's just.
It should work. I'll try it.
Finding the zero. And 0.8.
We didn't do it at 25. Or do it at 30.
I hear. Do it at,
Oh, I think graphing was an instant.
No, you grab the erase, the derivative, right?
Well,
Are you polar?
It didn't do it that early.
It's the angle, no question.
Yeah. Which one?
It's like number one and number two.
Mm-hmm.
Like, I see inconsistency. Number one, I don't know why these are like, why is that equal zero when it.
Right, so I would say if you're just dealing with, like a limason or whatever, that where there's no polar zero, then I just need to know where the starting and ending point is so I can get that full cycle. But anytime there is a loop or a pedal, then I'm looking to see where are two consecutive polar zeros going to occur. And if I can get two consecutive polar zeros to show up, I know that between those polar zeros will create that pedal or that loop. Yeah. So it doesn't matter. I mean, we could have used other intervals, but I just want to find the first two that I get to. Once I get to the first two, I know that if I get from polar zero to polar zero, it's gonna create that loop.
So 0 to pi wouldn't have worked here.
No, I wouldn't. Yeah. I'm So here for loops and pedals, I'm always gonna set equal to 0. So I can get that local. If, show it, yeah. I would play for. The last one.
The derivative. Those ways and I think like you're totally interesting, but one of the big gives you that as a number. It's like really very and so like. Look, if you go I look at the boundary right now, find zeros. Okay. How much should I support each one? Oh. It's just. There you go. Okay. Thanks.
Yeah, thanks.
So for this one, why would, it said this one was right, why would it be the six to? And why is it?
Because since it's regulated, it's the first version.
Well, it's kind of like the beginning part.
Because it is said that.
Yeah, if I'm going from fourth to first quadrant, I can't do 12, 5, or 6, 5, or 6 because
It's metric.
they're not connected, right? So
If it's
to
metric.
get from fourth to first, I have to go into the negatives.
So you
So that's why.
So these are in I, because it takes two cycles rotation.
Oh, it's like in the Y, right, there's like.
It's like this.
You have to be careful.
So this is a pedal, right?
Uh-huh.
This would be like.
This is my stuff that because it's review. It always
This would be like -5 or 6, and this is what's gonna set actually.
Yeah. Be safer to say. Graph shows area to 0 to 5. If you're safe.
It'd have to be a 4.
Yeah. That would be good.
Like,
It's super check. Yeah. We'll so we'll further. Yeah.
like, for example, like if it was. Anything about it, that's not percent this. You need to find like. The first.
Yeah, they do practice. You said. Our US 3 minutes by Friday.
Those cases, so like our cosine beta.
Our cosine beta, I use it 1 over 2 today, so you take the derivative of that. Because that's on the bottom. You got more area.
You guys, pick up tomorrow, but you guys can come get your phones. I want to put it on the board here. Thank you. Which number was that again?
Yeah, so again, the 0 is out. Yeah, you're right. That's good.
Talking about.
That'd be easier.
Negative two for. Oh, wait, why would we go?
Come over.
Oh, here you go.
That's like, you're like, I think.
Yeah, you're like, I guess take that.
5 minutes from now. Yeah.
Oh, so weird.
Always like.
That was devastating. I don't know, maybe, I don't think I put it in wrong.
Which number is that?
Yeah, I mean, it's like. You're under like that's for
Because, through this, is it kind of going backwards and causing that negative to show up? But yeah, it's always positive, always positive.
No, we're doing. Well.
Sarah, I love Sarah.
Well, you're just trying to get
Love
like.
Sarah.
So it's just like.
No, you can't.
Like 130 areas.
I'm looking at.
Yeah.
What do you think?
You're making it sound like that.
It's just kind of, it's like, why would you get that? As long as you make a very good extra, but it's.
Buddy.
I get it.
Yeah.
Oh.
Just like.
Sarah? Sarah. I know. Yeah. Like my favorite.
That's what he calculated.
Yeah, okay,
There's no way.
so here,
Wait,
I
I mean, just.
first off, we know that fourth quadrant is 11 pi over 6.
Yeah.
Right? But this is too far away, right? It's not connected to pi over 6. So we can always subtract 2 pi from 11 pi over 6 to get to negative pi over 6. And that's fourth quadrant. And if I play with these values here, plug them into the calculator, negative pi over 6 is at 0. And then 0 is going to be at 4. And then pi over 6 is going to be at 0. So it's going to start here. And it's going to, if we start our graph here, it's going to sketch the graph from this portion on. So normally the graph would start here and then it would do this and then it would complete the remaining portion here. But if we want to start here first, then it would graph this portion first and then this portion, and that will basically, this is still going to create that first that pedal, but just a little bit out of order because it's going to do the last part first and then the first part. Yeah. So that's how we can get it to the bounds from negative pi over 6 to pi over 6, filling in that fourth quadrant into the first quadrant. Yeah. Okay, so tomorrow I'll check up to page 49. Okay.
This solution appears twice for like a horizontal or vertical tangent. Do I cancel it?
Yes, it appears twice. Oh, guys, real quick, page 46, 49, but then also page 55 and 56 for the practice. I'll send out a reminder.
I'm gonna check. I might just not be like too. Maybe that they actually felt that. It's kind of like quickly.
Oh, yeah,
So I have everything else to through.
Okay.
Yeah.
And you could go.
So, but actually, what I'm thinking, you should just so that they know this. I'm not used to paying.
They know.
What's today?
Yeah.
But,
Two houses on top. I said you have to first.
Sounds good. Thank you.
wait, Mr. Frank, just to make sure, I meant like, so for just horizontal tangent, I'm not saying it shows up in horizontal and vertical. Just for horizontal, I say end up with two equations of theta. If it shows up in both, it still cancels.
All they said.
Oh, you shouldn't get repeats.
Okay. No, I
You
didn't.
shouldn't.
I was just
But,
asking the
but
case.
if it shows up as repeats, it should still be a valid,
Okay.
but technically we should be checking with vertical tangents as well, because anything that overlaps, we can remove it from the build.
Got it. Thank you. John.
Question.
Yeah.
For ants,